talk is leveraging Postclick Feedback for content recommendation. This is presented by Hongyi from Cornell Tech.
Okay, hello everyone, I'm Hongyi from Cornell Tech. I'm glad to be here to present our work on leveraging Postclick Feedback for content recommendation. This is a joint work with my amazing collaborators Longqi and also my advisor Deborah Estrin. So let's get started. Implicit feedback are being used for recommendation system to train and model user preferences. What we mean by implicit feedback is usually referred to user behavior such as clicks, views, and purchases, etc. They appear in large quantities and are really available for training machine learning or more recently deep learning-based models. However, implicit feedback is notoriously hard to integrate, especially when you consider recommending informational items such as videos, music, or news articles. Usually in those scenarios, the clicks are just the first impressions of users on those content without actually interacting with the content itself. So in those cases, for example, user might watch on video and click on it and then watch it for a few seconds and then skip the video. So instead of just simply integrating implicit feedback as positive feedback, we try to leverage this kind of post-click behavior to further disambiguate click and non-click items. So under our definition, this types of interaction that is from click and play-through behavior, we refer to them as positive feedback. Where in contrast, those click and skip behavior, we refer to them as negative feedback. So under this type of definition, we're trying to break ties among the click and non-click items by further fine-grain the interactions that happens after the user clicks. So we leverage two datasets, real-world datasets, to explore the feasibility of incorporating post-click feedback into recommendation algorithms. The first dataset is actually from Spotify, released through a data challenge that happens this year in Wisdom. So, and the second dataset is a short video that is released by ByteDance, or more accurately from their TikTok platform, which consists of like short videos recommendations. So they are both available through the links I show here, and they contain millions of user interactions beyond just clicks. They also show like whether users skip or complete certain items after clicks. So that is the dataset that we use for our experiments. So what we found from the dataset. So first, we find that the skip behavior is actually very prevalent across these two content domains. As we show here, the shaded area corresponding to like what's the percentage of user skips after they click certain items. And we found that on both datasets, more than 50% of the clicks are followed by skips. So which is kind of showing that users are not necessarily satisfied with the content. And if you look closely into the left column, so this is the skip rate sorted by the user, users. So basically showing on these two datasets, it's quite different. There's quite different user skipping behavior, and we speculate that the user skips on different content consumptions can be very dependent on the specific types of media type or like the content domains. And also we verified that the skip rate correlates with item popularity that we show here. The more popular items, there is like lower skip rate, but for long tail items, the skip rate tends to be higher. So we trained two classic recommenders, namely weighted regularized matrix factorization and Bayesian precise ranking on the click data alone. And then we evaluate the performance on two types of ranking tests. So test one is the standard offline evaluation test, which the recommender aims to rank the click items above non-click items. So this is essentially trying to re-implementing what the system already does right now. And the second ranking task corresponding to, we want the recommender to rank the click complete item over a click skip item. So this is essentially seeing what correlates to the end user engagement or user satisfaction. So in this table, we show the different performance on the two tasks. We can see that on both datasets, the first ranking test actually yield a pretty good performance, and people might be satisfied that we can correctly predict the clicks. However, when we evaluate on the second task, where we want to actually put the click complete items above the click skip items, we see a huge drop in the AUC of this task. So this is essentially saying what we recommend to the users currently, not necessarily resulting in them staying on the item for a long period of time, or they're necessarily satisfied with the items. Actually, they might skip the item a lot. So how can we improve? We propose a probabilistic framework to incorporate the post-click feedback signals. So we define three sets of items here, observation here. So the first type of observation is so-called positive observations corresponding to the click complete interactions. And the second set is so-called negative observations corresponding to the click and skip interactions. And the third set of observation corresponding to the non-click items. So under this characterization of the observations, we want to optimize the probability of certain observations under the model parameters using maximum likelihood estimation. So, a bit glitchy, but so we assume these three set of observations to follow certain Gaussian distributions with different variances. With those variances, we were able to kind of control the confidence we put on the interpretation of each set of items, so that we are not necessarily saying a click and skip is a negative user feedback. Actually, in some situations, there might be users saving the item for future revisit, or some circumstances that they are not essentially very accessible to the music player, so that they cannot skip the item. So it's kind of a noisy signal, so that's why we kind of use a probabilistic approach to interpret those signals here. And we kind of extend this on both the pointwise and pairwise setting. So under the pointwise models, the mean of the Gaussian distribution will be a model predicted score for certain user item here. And under pairwise setting, this is essentially can be interpreted as the probability of the item I being ranked above item J for certain user U. So the updated MLE objective can be written as the equation on this slide. We use the variances of Gaussian distribution to control the weights we put on different sampled observations from these three set of observations. So we show here some examples how to extend the pointwise model and later on the pairwise model. So the weighted regularized matrix classification is a very classic model. Here our extension for this model is basically we introduce three hyperparameters that can be tuned on a validation set that controls the weights we put on different set of observations. And we also introduce baseline extension where we manually fix beta to be 0. So those corresponding to case where you don't explicitly learn from the negative feedbacks, you are actually just correcting the labels for the positive set of observations. And similarly for Bayesian percentile ranking, the assumption here is that we sample from two pairwise sets. So the first step would be we ask the click complete items to be ranked above or preferred above the click skip items. And then the second step is that we want the click complete items to be preferred over non-click items. So this, we also introduced two hyperparameters here, alpha and beta, and we also test the case where we fix beta to be 0 and how does that compare with the case where we explicitly learn from this negative set of observations. So this is the evaluation on both datasets. First, we see that compared to the baseline model and baseline extension, there is a huge improvement when you explicitly learn from this kind of negative user feedback introduced by this post-click interactions. So we see overall for example, when compare Bayesian personalized ranking negative weighting versus the base model, we have a 90.4% improvement. However, if you look across these two data, which give us a more interesting result, on the video data set, the improvement is pretty much higher than on the music. So we have strong speculations on why this happens. Because video is generally a more engaging format of content that attracts user attentions than music, which is supposed sometimes to be played in the background. And also, there are various contexts when users listen to music, so that users click and skip is not necessarily a good interpretation of negative feedback in those cases. So we assume maybe integrating more user context and feature-wise context that we can actually improve our models further. So to briefly sum up, first we identified this misalignment between click and post-click user preferences, which shown in two large real-world datasets. And secondly, we propose a probabilistic framework to extend the current collaborative filtering algorithms, and this turns out to be actually quite easy to implement. So in practice, you can implement the reweighted function by just doing resampling of your training of your recommender. So you can imagine this framework can be also applied to deep learning-based approaches or other types of recommenders that you want to explore with. And last but not least, we show some improvements on the recommending for content-based recommendations, for example, on music and videos. And future work can look into different types of content, for example, like news articles or books readings, and you can find actually the concept of click skip is very extendable in those situations as well. So we've also put our codes on GitHub, and you can find it in our paper as well. Feel free to contact us if you have any questions. And with this, I conclude my talk, and I'm happy to take questions.
Thank you very much. I just love everything about Postclick. So did you think of normalizing by the actual time of the content? Because that could have removed some of the things that you found out.
Yeah, so I think we also have a little bit of discussion about the dwell time in the paper. So that's kind of related to this idea, which here we focus on the binary interpretation of whether the user skip or not skip, but the dwell time might be more sophisticated interpretation and actually help more when you consider specific context. Like, for example, when you listen to music, as a 5-minute song, you probably will define a certain threshold that can be classified as user engaged or user not engaged. And that also might be correlated with what happens before this session. So I think in those complex cases, this dwell time might help, but here we propose this general idea of just binary interpretation of the...
Because this could also explain the difference you've seen with like one type of content, which is video, which is longer, but short video and the...
Yeah, that's why like also we find here the short video, it's actually a strong indicator, but not necessarily might be in like a long video from YouTube, for example.
Okay. There's another question over here. There.
Hi, thanks for the talk. In the evaluation set, the click skip is considered as positive or negative?
You mean here, right? In test 2?
Yeah, in test 2.
So click skip is considered as negative.
Click skip can be positive or negative, and so how do you handle the cases where the users might have to listen to it, they are satisfied, they want to move on, and there is still a positive signal, not necessarily that not dissatisfied with this.
Yeah, so that's basically why we try to adopt this Gaussian distribution and use the variance to control like the weights we put on those observations. So example, if we, in certain types of data distribution, those cases might happen a lot where a skip is not necessarily a negative feedback, the weights will be pretty low in those cases.
Okay, let's thank our speaker.